It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Finding Doing Nice Coffee.
Hi guys, this video today is going to be all about triglycerides. Okay, so triglycerides are the category that we put both fats and oils into. And so I'm just going to first briefly talk about what a triglyceride is. Okay, so a triglyceride is actually an ester. And as the prefix tri indicates, it's an ester of 3 acids. And we always use the same alcohol to build our triglyceride. So if you're talking about the general structure of a triglyceride, we use this alcohol. So it's a 3-carbon alcohol, right? And each of the carbons has a hydroxyl group on it. So this alcohol, hopefully you can name this systematically. If you can't, 1, 2, 3 carbons makes it propan, triol, because there's 3 alcohols, and it's on the first, second, and third. So this is propan 1, 2, 3 triol. Now you will be asked to name this systematically, so make sure you can actually do that, right? And it should be pretty straightforward and second nature to you to be able to identify that the alcohol that we use in triglycerides is propan 1, 2, 3 triol. So because we've got 3 alcohol groups here, what we can do is we can bring in 3 what we call fatty acids. Okay, so fatty acids are the other thing that we use to make our triglyceride. Now, fatty acid is characterized by either 12 to 20 carbon atoms in length. So what you've got is you've got a really long carbon chain, which we represent by R, and then you've got a carboxylic acid group on the end of it there. Now that carboxylic acid group bonds to your 3 spots of your propan 1, 2, 3 triol or your glycerol, and so we get 3 esters being formed, which is why we call them a triglyceride. Alright, so first thing you need to be able to do is to know the structure of propan 1, 2, 3 triol. You'll also need to know what classifies something as a fatty acid, which is where it's 12 to 20 carbon atoms long. What you then need to be able to know is to be able to identify if something is a fat or if it is an oil. Okay, so over here I'm going to go through firstly about what a fat is. Okay, so a fat is a solid at room temperature. Okay, and they're commonly found in land animals. Okay, so they come from land animals. So if you think of things like pigs, all right, which have got lots of nice fat on it, which becomes like that most amazing of all foods of crackling. So land animals are our common source of fat.
What about bacon?
No.
Ham?
No.
Pork chop?
Dad, those all come from the same animal.
Oh, yeah, right, Lisa. A wonderful, magical animal.
They are termed saturated. Okay, so sometimes you might hear people talk about saturated, unsaturated fats, and what they're talking about is the number of hydrogens that are in there. So saturated means it contains the maximum amount of hydrogen. Right? So in terms of chemistry, what we mean there is there's no carbon double or triple bonds. Okay, so there's no alkane in there. It's purely all hydrogen. Now, what that looks like is you've got your propan 1, 2, 3 triol backbone. So this is just another condensed way of writing it. So I'm showing you it there. All right, and then we get our ester group forming over here. So this is where our fatty acids have come and attached themselves to the oxygen of the propan 1, 2, 3 triol. And then you've got these long carbon chains. Now, rather than writing out 12 to 20 carbon atoms, what we do is we use the stick version of it. And so you'll see it drawn like this. So it's just a zigzag line. There's no double or triple bonds in here. So we just get all these zigzag lines to represent the 12 to 20 carbon atoms long of our fatty acid. What happens here is you've got these 3 chains which all stack really nicely on top of each other. So I liken it a bit to like a can of Pringles chips where they just all line up. There's lots of interaction and contact between the chains here. Now, the interaction and contact between these chains is secondary bonds, and the secondary bonds that we get are dispersion bonds. So we get lots and lots and lots of secondary dispersion bonds occurring between the chains. When you have a lot of bonds, that means it takes a lot of energy to break them apart. means it has a higher melting point, which is why they are a solid at room temperature. Okay? That's purely due to the fact that in order to melt this, you have to supply energy into it to cause these chains to vibrate and break apart. You have to break the secondary bonds, hence a solid at room temperature. So that's a fat. So what's the difference between a fat and an oil, you may ask? So that's a good question. Hang on. Okay, so if we're looking at oils, oils are triglycerides as well. However, they are liquids at room temperature. And they normally come from marine animals. So if you think of whales, seals, so fish oil is very, very common that a lot of people take. So marine animals, and in the other place you'll also find oils is obviously from plants. So sunflower oil, canola oil, peanut oil, those are good examples as well. Now, these are called unsaturated, which means that they have carbon-to-carbon double bonds or triple bonds in there as well. Okay. Now, that has an impact upon the chain. So what you need to think about, I'm just going to draw this first here, is when you've got a normal carbon chain, you have a tetrahedral arrangement around every carbon atom, which is why when we were drawing our chains earlier, we had this zigzag up and down. Okay. However, if you introduce a double bond, so if we put a double bond between these two carbon atoms here, you no longer have a tetrahedral arrangement around every carbon atom. What you've now got is a trigonal planar arrangement around each of the carbon atoms. And so that changes your bond angle. So if we do it here, make this into a trigonal planar arrangement around our carbon atoms now. Okay, and so this one here is going to shift as well. So we're actually going to end up with, if this is our carbon that we're going to, if we then have a carbon-to-carbon triple bond there, right, there, and like that. So now we've got our tetrahedral arrangement around our carbon atom, okay, and then the next one is going to, if I redraw it so it actually looks like that, right, to the carbon atom here, tetrahedral arrangement, carbon atom here. And so you can see what we've done is we've actually changed the shape. Instead of having this nice zigzag line like this, we've now changed the shape of our chain by introducing a double bond in there. Triple bond obviously turns it into a linear arrangement around one of the carbon atoms as well, and so that changes it even more. What that does is that has the impact upon, with our carbon chain now of our triglyceride, if we draw this up, and I'm going to exaggerate it a little bit to try and make a point. That's what sanguines do. So if we put propan 1,2,3 triol at the start there, and then we make our triglyceride over here. Practice drawing these so you'll be able to do it quickly. What we get here is, if this one, let's just say this is our straight chain, that's what we had in our fat, but as soon as you start introducing your double bond like that, it's going to start to, let's say, change the shape of your chain like that. This one as well, if we introduce a triple bond in there, that's going to change the structure like that as well. And what you can see now is that we really don't have the same number of positions or spaces to be able to create these secondary dispersion bonds between the chains. So we'll get some there, but here the distance is too great between the chains because we've introduced this steric change due to our double and triple bonds. So because of that, we've got fewer dispersion bonds between the chains, which require less energy to break. Because there's less energy to break, we have a lower melting point, which is why they're a liquid at room temperature. Alright, so the difference between a fat and an oil is that a fat is saturated, contains a maximum amount of hydrogen, no double or triple bonds. The chains stack really nicely, lots of secondary dispersion bonds, which means a higher melting point. Oils, on the other hand, are liquids at room temperature because the chains do not stack nicely. Now, if you go through a process called hydrogenation, okay, so I'll write it up here, hydrogenation, what that means is you add hydrogen into it. Okay, so if you take a oil and you hydrogenate it, so you add hydrogen to it, what you're doing is you're actually going to force it to become saturated. So you're breaking the double and triple bonds on the chains, and what's happening is that your chains are now going to become nice and linear again, like they were in the in the fat, which means you're going to increase the boiling point. Okay, so if you take an oil and you add in hydrogen gas, all right, this is an equilibrium, you can go both ways. You turn it into a fat, all right, what you use is a catalyst, all right, so something like platinum's a really good one to use, all right, because that helps to increase the rate of the reaction because all organic reactions are slow, and you also use high pressure. Now the reason for that is due to Le Chatelier's principle. Over this side you've got a gas, that's the only gas within this, all right, that's a liquid, that's a solid. So the only thing that will be influenced by pressure is the hydrogen gas. So if you increase the pressure, it's going to go to the side with the least number of moles of gas, which is your product. So it's going to push your equilibrium towards the fat side. So that's hydrogenation. That's how you convert an oil into a fat, and you make it from unsaturated to saturated. Now, the last thing I'll talk about is just what happens and how when you hydrolyze an oil or a fat. Now, what you've got to keep in mind is that fats and oils are esters. So it goes through all the normal hydrolysis that you have for a ester. So you can do an acid hydrolysis using H+. Okay, so normally concentrated sulfuric acid is one that we use. Or you can do an alkaline hydrolysis using something like sodium hydroxide, a base. So if we go through and we look at hydrolysis, and I'm going to stick with the blue here just because it's my favourite colour. So if we look at hydrolysis, there's two types. Hydrolysis, get that right. So if we do H+, acid hydrolysis, the products that we get are propan 1,2,3-triol, 1,2,3-triol, so we get that, which is structure over here, okay? And you get your carboxylic acid, your fatty acid back, all right? That's just because you'd expect an acid to be produced in acidic conditions. However, if you do it under alkaline conditions, OH-, the products you're going to get are still your propan 1,2,3-triol. However, because it's an alkaline condition, as with any hydrolysis, whether it's an amide or an ester or a triglyceride, what you do is the base will react with that proton on your fatty acid, and so instead of getting the carboxylic acid, you get the carboxylate salt. So what that means is you have your R group with your carbon, double bond oxygen, and it will be deprotonated. All right, so you get the carboxylate ion, and then normally we'd use sodium hydroxide, so there'd be a sodium there as well. Okay. So you need to be able to understand hydrolysis. That I've covered in a lot of other videos as well, in particular about with amides and with esters, so make sure you can know that. The key things to know for triglycerides: what alcohol you use, propan 1,2,3-triol or glycerol is the common name, and fatty acids are 12 to 20 carbon atoms long. Difference between an oil and a fat is that a fat is saturated, has a higher melting point, it comes from land animals. Oils are unsaturated, they contain double or triple bonds. Okay, you can they come from marine animals and plants. All right, you can hydrogenate them, so you can add hydrogen across the double bonds to be able to turn it into a fat. Okay, and they have lower boiling points because there's not as many secondary bonds between the chains. You can hydrolyze them, so if you do it under acidic conditions, you'll get your alcohol and your carboxylic acid. If you do it under alkaline conditions, you get your alcohol and the carboxylate ion. All right. Hopefully this makes sense for you. The final thing I will mention is that you can also determine what's called the degree of unsaturation. So I'm just going to quickly explain what that means. And I think I've mentioned this a little bit before in some of the other videos, but I will just cover it again quickly here. So degree of unsaturation is determining how many double or triple bonds exist in a particular fat or oil. So I think when I go through and talk about alkanes and alkenes, I've talked a little bit about degree of unsaturation and how you test for it, but I'll just go through it again very briefly here. All right, it's a shame I don't have a different colour pen I can refer to, but that's all right. So with degree of unsaturation, what we're trying to determine there is basically how many carbon to carbon or carbon to carbon triple bonds we have, so double or triple bonds. All right, And what you do is you titrate it against, normally we use iodine or we use bromine. So iodine is purple colour, purple violet, and bromine is orange. You titrate it until you get your first permanent colour change. Now in this one here, it's either going to be colourless to like a pale purple or pale yellowy orange colour. So it's like doing a normal titration, okay, in terms of you titrate to your first permanent colour change. And the chemistry behind it is this, is that a double bond like this, when you're adding in iodine, your iodine adds across the double bond to form a single bond like this. Okay, iodine there. And every 1 mole of iodine you add in equates to basically 1 double or triple bond within your fat or oil. Well, it can only be within your oil, sorry. So you can determine the degree of unsaturation by doing a titration with iodine or bromine, looking for your first permanent colour change. Whichever one requires more iodine or bromine, assuming you start with the same stoichiometric quantity to begin with, is the one that has the higher degree of unsaturation. Alright, lots to cover in this one with triglycerides. You might want to break it up into 3 sections around the structure of triglycerides, then the difference between fats and oils, and then hydrogenation and degree of unsaturation and hydrolysis at the end. Hopefully it's helped. As always, if you've got any questions, just ask. Thanks guys.